So this is a slideshow for Unit 9 to kind of start reviewing our gas laws so that we can apply stoichiometry to gases. So far we've applied stoichiometry to solids, but we need to be able to apply them to gases and liquids, so this will be our application to gases. So to begin with, we need to kind of review our gas laws. Remember, when we were doing gas laws, there were 4 properties that we studied. It was pressure, which was the collisions of the particles with the sides or the walls of the container, how the volume changed depending on if it was in a flexible container or if it's a rigid container. The moles would be the quantity or the number of particles that are in the container, and then the temperature had to deal with the speed of the particles, and we used vectors to represent that. So we're just going to review quickly those gas laws. So a couple of things that we had to deal with gas laws. We know pressure units, there are several different ones, so we're going to kind of have to be able to convert between those. And then we also had to convert Kelvin temperatures or Celsius temperatures into Kelvin, because those are the way that we represent the relationship between pressure and volume comparing to temperature. It has to be in kelvins to get a graph that is linear. And the last one is, when we measure a gas, to do a comparison, we have to have our model for comparison, and that's called STP. And so that's standard temperature and pressure. And that standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere, or any of those other conversion factors. That is what sea level is. So just to review these quickly, we did Boyle's law, which relates pressure versus volume. Remember, this was the inverse relationship. As pressure increased, volume decreased, and I have my arrows here showing that. And so I just wanted to do a problem. Remember, we used these tables that we had before, and so on these tables we would record what our initial variable was and then what the final one was, and then we would set up the ratio once we knew what the effect was. So in this one we have a sealed balloon. It's filled with 2 liters of gas. So initially I have 2 liters of gas and I'm at 3 atmospheres. They want to know if I reduce the pressure to a 1/2 atmosphere, and I'm not going to change the temp, so this is going to be constant, and this balloon is sealed up, so I'm not going to let any particles in or out. I want to know, what is my new volume? So we know this is an inverse relationship, so we look at what's happening to the pressure. It looks like it's going down. If the pressure is going down and this is an inverse relationship, that should make the volume increase. So I need to set up my relationship. So if I start out with 2 liters of my gas times, and then I'm going to multiply by my ratio, I know I need to make it increase. So I'm going to put 3 atmospheres over a 1/2 atmosphere. Do my math, I get 12 liters. There's my answer. Okay, so remember doing these. We're just going to review these quickly, and then you have a review worksheet in your packet. The next one was Charles' law, how it relates temperature and volume. At this one, the pressure is remaining constant. And so as the temperature increases, the volume increases. We're also saying it's a sealed container. So this is a direct relationship, so we're not letting any more particles in and out of the container. So a problem sample would look something like this. I have a 600 milliliter sample of nitrogen in a flexible container. It's heated from 27 to 77 degrees Celsius at constant pressure. What is the final volume? So looking at this, remember, our temperatures have to be in Kelvin, so I have to add 273 to those 2 temperatures. So 27 plus 273 is 300 Kelvin. And then I'm going to raise it 77 up to 77, that is 350 Kelvin. Now they're telling me the pressure is staying constant, and it's a flexible container, and it is going to be sealed up, so we're not letting anything in and out, so it's also constant. And the volume I start out with was 600 milliliters. I want to know, what's my new volume going to be? If I look at my temperatures, it looks like they are increasing. Direct relationship for this one, this is also increasing. So to set up my problem, I'm going to start with 600 milliliters of my gas times, I want this to increase, so I'm going to go 350 Kelvin over 300 Kelvin. I'm going to multiply it by a ratio that's going to give me a larger number. My answer is 700 milliliters. So that was 2 of the gas laws. I'm not going to work a problem for every one of these, but I will just run through them briefly. The next one, the third one, was Gay-Lussac's, which relates pressure and temperature. And that means that you would have to keep the number of particles and the volume the same. This is another direct relationship. Notice our temperatures have to be in Kelvin to get this to run through 0, 0. The last one of these gas laws is Avogadro's, which relates volume in moles. So as you increase the moles, the volume of a gas will increase. And this would mean that you're going to keep the temperature constant and the pressure would be kept constant. Another direct relationship. You can see by my arrows. As one increases, the other one increases. Now, the last one that I'm going to cover on here is Dalton's law of partial pressures. And it states that the total pressure for a mixture of gases is equal to the sum of the partial pressures of each of the individual gases. So we're saying the total pressure of all of the gases just equals the pressure of the individual gases. And then we could have more than 3 in there. I just did 3 and said etc. So remember, pressure is related to the collision of the particles with the walls or the sides of the container. Therefore, it can also be related to the mole ratios, because as you have more moles of something, the particles are going to be in there, more particles are going to be in there, and it is going to cause more collision, which would be more pressure. Okay, so this one says, if you had a mixture of gases, if it contained 0.75 moles of nitrogen, right? So if I had 0.75 moles of nitrogen, and I had 0.30 moles of oxygen, and then I had 0.15 moles of carbon dioxide. And they told you the total pressure for all of this was 1.56. They want to know what's the pressure of each one of those gases. So the pressure is the ratio of the moles of each part to the total. So if you add up all of these, the total moles that you have in there are 1.2 moles. So this is the total. And so each one of these is the ratio of that to the total, the ratio of the mole ratio to times the total pressure. So if I wanted to figure this one out, I would just take 0.75 moles of nitrogen divided by the total moles to see what fraction it is of the total, times the total pressure, 1.56 atmospheres. This is going to give me what percent ratio it is of the mole ratio, and that mole ratio is equal to the ratio of the total pressure. So when I multiply that, I get it's 0.975 atmospheres, and I'm going to label this as nitrogen. So for oxygen, I'm going to take the partial moles, compare it, so moles would cancel out, compare it to the total moles, because I want to see what part of the total this is, times the total pressure. This gives me 0.39 atmospheres of oxygen. And the last one would be 0.15 moles of CO2 divided by the total moles present in the container times the total pressure equals 0.195 atmospheres for carbon dioxide. Okay. If you look at your moles, this is the least moles. It's going to have the least amount of pressure. This had the greatest moles. It's going to have the greatest amount of pressure. Okay. You can even look at this to this is a 2-to-1 ratio. So this should be half as much, and it is. If you add these up, add up this, this, and this, it should equal this 1.56. Okay. That's kind of our mole, using our mole ratios to calculate those.